What's up, guys? This is homework help here for position versus time graphs. We're going to check this out. I'm going to graph all of these. We're going to go over each one. I'm going to try to make this quick. So feel free to pause and fast forward as you need. We've got a skateboarder, or a roller skater, rolling down a marked sidewalk observed at the following positions and times. I've went ahead and graphed those in Desmos. I have them graphed here. Check that out. You can go ahead and create a table. I graphed all of the ones for this homework assignment on the same graph, and you can turn on and off the different pieces by clicking the circles next to them. So we've got that there. You can also zoom fit it to the grid if you click on the little zoom mark. You got to have it on, all right, but you can click that. Mine is up here. And it'll zoom it to that specific graph. So you guys can use that if you need to. So we've got it right there. We need to answer some questions. We've plotted the data. That's A. B, how can you use the graph? Well, I can just look at the graph for this question. That's pretty simple to do. I can just look at it at t equals 6. I can go up to 6. I can find that point. And on Desmos, I can actually just click on it right there. And I thought it would let you give a point. There you go. If I want to put that point on there. All right, 622. So I can figure that out. Determine how far he was. I can explain how to do that. Write the mathematical expression. Here it is. Y equals mx plus b. We've got our slope of 2 meters per second. We've got the y-intercept of 10. Where did I get that from? I did the regression line. All right, p, and then I used this little tilde mark. That's the key right below your escape key. And that helps me in place of the equals. I got m. That's the slope. T is my variable on the x-axis plus b, and it'll give me m as 2, b is 10. So when I write my equation, I put the units in and I write it out just like this, matching that y equals mx plus b portion. Was the speed constant? Absolutely. The slope is constant. The speed was constant. Check out the slope. There it is. Slope is the speed. Slope is the velocity. Remember, velocity and speed are basically the same thing. Velocity just includes the direction. So this is a positive slope of 2 meters per second. Number 2 has you graphing again, a different graph. That's the graph you see here. I've switched that around. Position versus time. Again, we've got a similar graph, similar pattern. You can see what's going on there, and they've got some questions for you. Just add the table. That's up here. You can put that data in. All right, it asks you how far from the origin was the skater at 5 seconds. 5 seconds. Once again, I can go here to 5 seconds, which should be right in between 4 and 6. Right about there, as you can see it popping up there. Looks like it's about 19, 519. 519, so 19 meters. And I did that by reading the graph. All right, just kind of tracing it along. Was the skater's speed constant? Yes, it was. How much was it? This same thing. We do the fit. This one I called P2 and T2 for problem 2, position 2, time 2. All right. The slope is 3. The y-intercept is 4. Slope was 3 meters per second. Previous one was 2 meters per second. So traveling faster. Was the skater was further along at 2 seconds than he was in the second trial. Does this mean he was going faster? All right, I didn't write that answer down, but no, he was not traveling faster. You can see their speeds. It doesn't mean that they have to be at the same position at the same time. Number 3 is asking you to graph another set of data. All right, and I went ahead and did that. We'll check it out here. All right, we went ahead and graphed that data, that second set, and we get something a little bit different. We can't put a curve fit or a regression line on this. It's not all one line. But it's still the motion of the object if we checked it every 2 seconds like we did here. Questions they're asking about it. What is happening during 4 to 6? 4 to 6 seconds. That's this area right in here. All right, what's happening there? It's not moving and not changing position. You've got this section here that's not changing. He's at position 4 the entire time during that time. So that means that they are stopped. The skater is stopped. What do you think is happening during the interval of 6 to 10? All right, 6 to 10 is right here in this area here. All right, what's happening there? It's a downward slope. That means they're traveling in the negative direction. They are not necessarily slowing down. They are not necessarily traveling faster or slower. They're just traveling in a different direction. All right, if I looked at the slope, I would say they are traveling a tad slower. All right, they had the same amount of time, 4 seconds, to cover less position. So traveling in the negative direction. Determine the average velocity. Average velocity, I kind of did the calculation there. That doesn't need much explanation. Average velocity uses displacement. Displacement is where we started versus where we ended. It doesn't matter what path we took. If you remember Toto and Dorothy, Toto traveling around, running around all over the place, that path length divided by the time it took would be the average speed, which is the second question. They're asking you to do that. It's the path length. How do you determine the path length for part E? Well, I go back to my graph and I can figure out how far they traveled each time. Traveled 4 meters in the first part, traveled 2 meters here, and traveled 6 meters here. So 4, 2, and 6, that makes 12 meters total. 12 meters is the distance traveled, the path length divided by the time. You get a little bit of a different speed. You got average speed and you got average velocity. Those two are different. What situation might be better for speed? What might be better for velocity? Go ahead and answer those on your own. And let me know on Remind if you have any questions.